Okay. So combinations and permutations. Can you tell me what the difference is between those?
So I know use a combination when like the order doesn't matter, and use a permutation when the order does matter.
Good. So can you give me an example of that?
The question on screen here about the jury, that would be a combination because
Good.
all 12 people on the jury are equal.
Good. All right. So have you learned about Pascal's triangle yet?
Yeah, we did today.
Okay, so you get how that's a cool little trick, right? Okay. So how many jurors are possible if you need to choose 12 jurors from a pool of 60? So this would be one way to write it is 60, choose 12.
Okay.
And do you have the formula for combinations?
I think so.
Because off the top of my head, I don't remember what it is. It has factorials in it. I know if you have a graphing calculator,
Yeah, you can just put it in.
and your teacher lets you do it, you can just put that in, right? Does your teacher let you do that?
Yeah, they do.
Okay, so do you know how to do that? That's in stat, I believe. No, maybe not stat. Calculate. No, it's not stat. Math.
I think
can't remember.
it's in
Variable stat. I've actually never done it on this exact online calculator, which is slightly different from yours.
Here it says you go. You press math, arrow RB.
Math, and then what? Oh,
the PRB.
Yeah, probability. There you go. So it's NCR.
Yeah.
So you type in the two letters, and it gives you your answer.
Okay. Is that it? Or
yeah, let me see. Combinations. I believe that's it.
Okay, so I just write that number and then possibilities afterwards.
How many juries?
I found the formula.
Yeah. So what's your formula say? Let's test that as well.
For combinations, it's n factorial over r factorial.
So n is 60.
Yes.
60 factorial over 12 factorial times
60 minus 12.
So 48 factorial. Is that in the bottom?
Yeah. And here the factorial sign is outside the parentheses, but inside. I don't know if that matters.
Okay, so tell me again. It says here, let me write the formula down. NCR equals n factorial over r factorial times n minus r factorial.
Yeah.
Okay, yeah. So that's right. You don't really even need these parentheses. I was going to write. I was at first going to write the subtraction, but I didn't. So the other way you could do it is you could use factorial, which is probably also in math probability. Yeah, there's your factorial. So 60. It's kind of a pain to do this, to be honest with you, because you got to go back to the factorial every time unless there's a shortcut for it. I don't see a shortcut for it on here. 50 math probability factorial. So there's 60 factorial divided by, and then you'd have to put parentheses around it so you don't mess up, 12 factorial times 48 factorial. And see how I got the same answer?
Yeah.
So just use the shortcut.
Okay.
You got the ability, and if your teacher doesn't mind. But that's a lot. Notice there's a lot of people.
Yeah, that's a lot. I'll just do the one on the top instead.
Mm-hmm. Is it a math somewhere where you can punch it in and it'll tell you the right answer or not?
Sorry.
Are you allowed to punch that in and it'll tell you if you got the right answer? Or are you just doing it like on a piece of paper?
Doing it on a piece of paper right now. But there might be an answer key.
Yeah, it's always good to just check, make sure you got the right answers.
It's 1.399 times 10 to the 12, I think that's
yeah, that's the same thing. So that's just the scientific notation is what they're writing, but our calculator has, the ability to write it out because it's a bigger screen. So number 4 on the next page, a standard deck at 52 cards has 4 suits and 13 different cards. You know that, right? You understand poker deck?
Yeah.
Okay. If the order in which the cards are dealt is not important, how many different 5-card hands are possible? How many different 5-card hands are possible? So this is a probability. So the first card, how many choices do you have for your first card? So a good way to do this is to think about 5 cards like this. And how many ways could you deal the first card?
26.
No, there's 52 different cards in the deck.
Oh yeah.
There's no
51.
There's no doubles. That's right. And then there's only 51 left. And then there's only 50 left. And then there's only 49 left. And then there's only 48 left.
Okay.
So it's basically that 52 times 51 times 50 times 49 times 48. There's your 5 deck card, and that's how many ways you can deal it. 311,875,200. That's how many different hands that you can deal.
Okay. It says on the answer key 2598960.
It says what?
It says 2598960.
That's what it says?
Yeah.
The order in which the cards are dealt is not, oh crap. Yeah. Because what I didn't factor into that. Yeah, I did that wrong. My bad. That is not correct. Because what I didn't realize is that I added in permutations of those as well. That was the number of permutations. So bad example. All you really have to do here, I'm an idiot, is 52 choose 5. That's all you need. 52 choose 5. Because the order is not important. So it's 52 choose 5.
Okay.
So let's go second enter, second enter, second enter. So it's 52 choose 5. 2598. Yeah, that's it. 2598960.
Okay, so the first number is always going to be how many total, and then I decide whether or not it's a combination or a permutation, and then the last number is going to be how many I want.
Correct. How many you're choosing. So 52 items and you're choosing 5 of them. How many ways can you choose 5 out of 52 items? That's what that is. Now it says how many 5-card hands consist of 5 cards that are all the same color. Let's see, how many 5-card hands consist of 5 cards that are all the same color?
I think here they're cutting it in half. It says 26 C 5, and then they're doing that twice.
Yeah. So what you're gonna do is this. Yep. For the red cards, there's only 26 red cards, and you're seeing how many ways can you choose 5 of those. And then you're gonna add that to the number of ways you can choose 5 of the black cards.
Okay, so it's just like the same thing.
Yeah, so there's 2 distinct possibilities. You can have 5 black card hands, and so there's half of the deck are black, right? So 26 choose 5. That's the total number of ways you can have a handful of just black cards. And then that's also the same number of ways you can have a handful of red cards. And you add them together because they're mutually exclusive. Like you can't have them at the same time. Does that make sense? So you just multiply by 2 basically.
Okay, yeah, I think that makes sense. Yeah.
With probability, it's always tough to kind of wrap your head around it. Like, what is it exactly asking, and how can I get to that answer? Like, what's the best way to get to that answer? A lot of times there's more than one way, but the best way sometimes it's hard to figure out.
Yeah, I was realizing that in class. Like I was kind of what they're asking.
Right. So 12 permute for basically means, I like to think of it as I've got a president, a vice president, a secretary, and a treasurer. So 12 choose for wouldn't distinguish who is in what role. But if you have a different role for everyone, then there's a lot more possibilities for this. So 12 permute. Okay. And this one actually is, I believe you can just go straight with, I believe this is just 12 times 11 times 10 times 9.
So it's using permutations because president's above vice president.
Right, because they're different.
That matters.
Yeah, because they're different roles. So if you had like people A, B, C, D, for combinations, A, B, C, D is no different than B, A, D, C. Those are the same for combinations. They don't count that. Combinations doesn't count that, but permutations does. 12P4 counts them all separately. So A, B, C, D, A, C, D, B, A, D, B, C. Those are all different.
Okay.
Right, and then A, B, D, C is even different, and then A, C, B, D is different. Like you can keep going like that. There's a lot more for permutation. So for this one, if you choose your president first, then you have 11 people left to choose your vice president, and then 10 people left to choose your secretary, and 9. So that I'm pretty sure works. So let's see if it does. 12 times 11 times 10 times 9 is that. And if you did the permutation trick, if you said 12 permutate 4, yeah, you get that same answer.
Okay, yeah, that makes sense.
So what I was showing you the last time, I was confusing it. I was doing permutations, not combinations.
Okay.
So that first thing I did was kind of messed up. So again, for this one, now this is one where you could even use Pascal's triangle if you want. It's not a bad idea to just have Pascal's triangle sitting. 1 1 1 1 2 1 1 3 3 1 1 4 6 4 1 1 5 10 10 5 1 1 6 15 20 15 6 1. And so since I got to 6, that's my, oh no, that's not. I got to get to 10. My bad. I got to get to 10. So 1 7 21 35 35 21 7 1 1 8 28 56 70 56 28 8 1. Do you know what I'm doing? 1 9 36 70 84. Did I do that right? 84 1. Yeah, it's getting kind of tricky, but anyway, if you wanted to do 10 choose 6, well, let me just do a simpler one. That's a little bit too long, but up to like even set 6 or 7. If you had like 6 choose 4, you go to row 6 and choose, this is choose 0. This is 1 2 3 4. So it's this one right here.
That seems a lot harder than just like plugging into the calculator.
Well, yeah, it is harder, but if you don't have a calculator, this is easier.
Okay, yeah.
If you always have a calculator with you, then sure, just plug it in, right? Why not? Heck, ask Google. But if you don't have that resource, it's good to know kind of a shorthand way of doing it. So and also the good thing about this is if you have your triangle just sitting there, if you've got Pascal's triangle up to like, let's say 10, then all you have to do is look at your triangle and just go over and be like, oh, there's 6, there's 10 choose 6, 10 choose 0, 10 choose 1, 10 choose 2, and then 10 choose 6 is going to be right there. So it actually, Pascal's triangle, if you already have it written out, if you have it, it's actually pretty simple.
You mean like if they give it to me in the test?
Yeah, or if you decide to, if they say, hey, you can't use a calculator, then draw out Pascal's triangle and boom, there you go.
Okay.
So again, P or 21 choose 5. You can, 2 ways you can do it. You can just go 1 2 3 4 5, and you go 21 20 19 18 17. Or you can punch it into your calculator. Whichever way is easier, doesn't matter. So hit second enter right here, and then you can just arrow back. Since I've already got 21, choose 5, or you could have done 21 times 20 times 19 times 18 times 17. Same answer.
Okay. So we can skip number 6 in those 7.
How many different ways? You're going to toss 10 different coins. How many different ways will at least 9 of the coins show heads? Okay, so this is another one of those tricky ones. You got to kind of think through a little bit. 10 different coins. Okay, so when you have something like this, a lot of times it's better to do the opposite, or to do the to do like the opposite. They don't call it the opposite in trig or in probability. They call it the complement, I believe. So what's the complement? What's the opposite of this? How many days will you get at least 9? So another way to say it is, this the same as saying, how many ways will you get exactly 1 tail? You see how that makes it a little bit easier?
No, I don't understand that.
So to say how many different ways will you get at least 9 of the coins showing heads? Oh no, that's not actually what I said is not right. At least 9. you could say, how many ways can you get one or zero tails? At least 9 heads means you have 1 or 0 tails.
Yeah. Because
Does that make sense?
10.
Yeah. So that's just easier to do it that way. So how many ways can you get exactly 1 tail?
You mean like how many times do I have to flip it?
Yeah, let's see. You're going to toss 10 different coins. How many ways can you get exactly 1? Think about what that would be. I think it's going to be 10. It's going to be 10, choose 1 plus 10, choose 0. Is that right? Or is it permutations? No, I think it's combinations. Because the order doesn't matter. So 10, choose 1 is 10. And 10, choose 0 is 1. Is the answer 11?
It is, yeah.
Yeah, that's how you do it.
So I don't really understand what that means. How you got that?
So I'm showing you how a lot of times with these problems, it's easier to, when they ask a question, ask if there's an easier way to state that question. How many different ways will you get at least 9 coins showing heads? That means you have either 9 or 10 showing heads, right?
Mm-hmm.
So if there's either 9 or 10 heads, how many tails are there going to be?
1 or 0.
There's either going to be 1 or 0 tails, right? So it's just easier to think of it. It's easier to do these problems than in my head than to do these ones. They're technically the same, but in my head, it was easier to think of it that. We could have also done instead, we could have done 10, choose 9 plus 10, choose 10, and the answers are going to be the same. This is 10 and this is 1.
Okay.
Right? But that's what we're doing. That's how we're doing that problem. So now let's talk about this. How many different ways can you get flipping a coin? You're flipping all 10 coins, right? How many ways can you get only 1 head showing? Well, it could be you're tossing 10 different coins. There's 5, 6, 7, 8, 9, 10. So it could be tails, head, or head, tails, head, or head, tails, head. You get what I'm saying?
Yeah. It could be anyone.
So there's 10 ways. There's 10 locations. Like think about each coin on its own, right? All the rest are heads. So you're flipping 10 coins and you're choosing only one of them. I don't know how else to explain it. So sorry.
I think I understand.
It's very hard to explain as well. And sometimes my explanation isn't even always necessarily the best way to explain it. But this is the problem with probability one for me is it's not something that you do a ton of and you just kind of it's a logic a lot of times, right? So it's good to know the formulas, but when it comes down to sometimes it's just logic. So let's try the next one, see if this will help explain it. How many different ways will at least 4 coins show heads? So at least 4 means So that means it's either 4 heads or 5 heads or 6 heads or 7 heads or 8 heads or 9 heads or 10 heads. Right?
Yeah.
Which means, yeah, I guess that's what you can do. So how many
greater than or equal to 4?
Right. So how many ways can you have four exactly showing heads? Is this right? Could you do 10 choose 4? Yeah. 10 choose 4 would be 4 heads exactly.
Okay.
So 10 choose 5 would be 5 heads exactly.
And
10 choose 6 would be 6 heads exactly, etc. So it's 10 choose 4 plus 10 choose 5 plus 10 choose 6 all the way to 10 choose 10.
So I just add them all?
Yeah. And that's another example where if you had Pascal's triangle, it'd be easier because you can just look at them and add them together.
Yeah.
And let's see if that's right. Let's see if that works. Do you have the answer key?
Yeah, it's 848.
Okay. I don't know if there's a shorter way to do this one, but 10 choose 4 plus 10 choose, this is kind of a pain to have to do.
Well, that's what they're doing here. They're just doing what you did.
10 choose 5. Oh, they're showing you the work?
Yeah, this one that shows you.
10 choose 6. So that is correct, right?
Yeah.
10 choose 6 plus, and again, this is where Pascal's triangle, right, would actually be a little bit quicker because you've got them all right there. Plus 10 choose 7. Well, you can see what the answer is, right? I don't really have to do this.
Yeah.
Plus 10 choose 8, 10 choose 9, 10 choose 10, and then just punch it in. Okay?
Mm-hmm.
All right, let's see. You have another one? William Shakespeare wrote 38 plays that can be divided into 3 genres. Of the 38 plays, 10 are histories and 10 are tragedies. Okay, and so the other genre would be what, 18 of the other genre? Oh, maybe they told you. What was 18? Comedies?
Yes,
Yeah.
comedies.
How many different sets of exactly 2 comedies and 1 tragedy can you read? So you're going to pick exactly 2 comedies. So there's 18 comedies and you're going to choose exactly 2 of them. And then you're going to pick 1 tragedy. But what we're going to do is multiply this now. We're going to multiply this, not add it. And I forget what is it the multiplication principle of probability? You probably learned it. And 1 tragedy. And how many tragedies? There's 10 tragedies and you're choosing 1 of them, which is just 10, by the way. So 18 choose 2 times 10 choose 1. And that would be your answer. 18 choose 2 times 10 choose 1. Is that what your answer says?
Yeah.
18 choose 2 is that times 10 choose 1, which is just 10. So it's 1530. That's the right answer?
Yeah, that is.
Okay, now the last one says, how many different sets of at most 3 plays can you read? How many different sets? Huh? I don't get the question. How many different sets of at most 3 plays can you read? So there's a total of 38 plays. And we're going to choose 3 of them. But we don't have to read 3 of them.
You could do 2 or 1 or 0.
Yeah, we can also choose, See, this is where it's kind of hard to tell. Am I adding 38, choose 2, and 38, choose 1, and 38, choose 0? Meaning if like you read A, B, and C, that counts different than just A and B and just A and C, because that's what I'm doing here. And that counts different as just A or just B or just C. So all of these would be counted separately, which I think.
So how do I know if I have to add or multiply?
Well, for this one, you multiplied because you're choosing the comedies first, but then after you choose the comedy, you can combine that with any of the tragedies. So you have to multiply it because you're doing two, you're choosing I don't know what words to use for this exactly, but it's called the multiplication principle. I'm not good with the wording, the verbiage of probability, but it's like you're doing like the outcome. You're performing one outcome after the other or something like that. Look in your notes and you will see it. Like you're performing one outcome after another, you multiply or something like that. Whereas for these ones, and I don't think that they're talking about mutually exclusive quite yet, but for where was the one that we did before? For this one, you're not multiplying because you're not picking 5 cards and then picking another 5 cards, right? You're choosing, there's at most 5 cards, so you're going to have either 5 cards. These are mutually exclusive. Maybe they do use that term. Picking a set of 5 red cards is mutually exclusive, but from picking a set of 5 black cards. Those are 2 separate events that you're doing, not one after the other.
Oh, okay.
Does that make sense? I don't know if that's the right way to say it, but if you read it, they'll use some verbiage in there that maybe is a little bit more concise, a little more clear.
Yeah, I think that makes sense.
It is tricky. This is kind of tricky stuff, but when you see words like at most 3 plays, well, I can choose. So the events are choose 3 plays, right? Or choose 2 plays, or choose 1 play to read, right? You see how those are separate events?
Yeah.
Or choose none. So there's one way to choose none, right? You know, this is just one. You could just say, hey, I'm not going to read any of them, right? Or you can say, hey, I'm going to read, this is 38, because there's 38 ways to choose 1 play. If you have 38 plays, choose only one of them to read. And then how many can you choose to, right? So hopefully that makes sense.
Yeah, I think it does.
All right, man. Well, hey, good luck with this. Thanks for being flexible. I got something to go with my son today at school, so able to head there.